A very good evening to everyone. Welcome back to my session. In the last session, I've talked about absorption of electromagnetic radiation by molecules. Today we will have a look at the working principle of UV visible spectroscopy. Before we go into the working principle of UV visible spectroscopy, I would like to recap about how colors are produced by the presence of conjugated system. If you remember, we have seen in the theory of colors in the fourth semester where we discussed about width theory, resonance theory, and also the molecular orbital theory. So I'll put a link in the description to my lecture on width theory. That is the theory about chromophores and auxochromes. But today we will revisit only the molecular orbital theory. That's a very important theory to understand about the UV visible spectroscopy. But before that, let's have a look at the following 3 food items we encounter in our daily life, and how from there we'll pick up about how colors are produced. So we have tomatoes, carrots, and egg yolk. These 3 items has 3 distinct color. We have the tomatoes in red color, the carrots in orange color, and the egg yolk in yellow color. Interestingly, all the 3 food items contain 3 different organic molecules as pigments, but they are rather very similar to one another. So the 3 molecules, they are lycopene in tomatoes, then we have beta carotene in the carrots, and we have the third one, that is lutein in egg yolk. One common pattern about these 3 molecules that you can see here is that we have all the 3 different molecules conjugated alkenes. So what does this mean? If you still remember about the width theory, if you recollect, all these colors, as per width theory, colors are caused by the presence of unsaturated system in a molecule. So for example, now let's go back to one important thing. Colors are produced by the presence of conjugated double bonds. Now, when a molecule absorb light at a particular wavelength, the color produced is not the color that it absorbs. Suppose it absorbs in a blue light, it will not produce a blue color because that light has been absorbed. So it will produce a complementary color. Then, knowing the complementary color, we will know which region the molecule absorbed light. Now let's have a look at the color wheel given by Isaac Newton. Now if we look at this color wheel, Isaac Newton, if this is an orange region, if a molecule absorbed in this region, the color observed by us will be somewhere opposite to that, so it will be blue. If a molecule absorbed in the blue region, it might have an orange color, depending. If it absorbs somewhere here, it will be red. Okay. If it is indigo, it could be yellow. If it is violet, then it will be the complementary color. So let me just superimpose the different color circle using, I have just make some changes. This is the original Newton's color circle. So let me just superimpose that. Now here we can clearly see, if suppose a molecule absorbed somewhere in the blue region, you will get the color in here. So for example, lycopene absorbed somewhere all these regions, so it is red in color, and then beta carotene is absorbing somewhere in this region, so you get this orange color, and then the lutein absorbs somewhere here. So difference in absorption. But what's important is that many molecules, they are not colored. So the question is, why? Even though they contain double bonds or conjugated system, the molecules are not colored. Most of them, they are not colored. So to try to understand that, let's look back at the molecular orbital theory. So here we'll take the example of a formation of a hydrogen molecule. In the formation of a hydrogen molecule, if this is the energy, then we have two hydrogen atoms, let's say HA and HB, containing the atomic orbital, which is the 1s orbital here, and we have these two electrons, one electron on HA, one electron on HB. So these are two hydrogen atoms. Now if suppose each of these electron is defined by a wave function psi HA and this one is by psi HB, there's one approximation which is known as the linear combination of atomic orbital. That means the atomic orbital simply combine to form a new molecular orbital. So in this principle, what is important is that the number of molecular orbital will always be equal to the total number of the atomic orbital. So here from two atomic orbital, we have two molecular orbitals. Now these molecular orbital will again follow the same principle. So we have the electrons now will occupy the molecular orbital, in this case the lowest energy molecular orbital. So this lowest one is known as the sigma bonding molecular orbital. So it's a bonding molecular orbital. Then this one here is a sigma star, which is also known as an anti-bonding molecular orbital. So this is the molecular orbital. So now let's eliminate all these this atomic orbital, and we'll just look at only these molecular orbital now, because this will concern us about the absorption of electromagnetic radiation. So here this molecule, that is hydrogen molecule, both the electrons are present in the ground state. If we take this in a simplified form, we can call this as the molecule is in the ground state of its electronic state, because it involves electrons, so it is an electronic state. So now what happens is that when an energy is absorbed, you see the difference in energy between these two, the bonding and the anti-bonding molecular orbital, is equal to h nu. Now here nu is the frequency of the radiation. So if a frequency of radiation is equal to this difference in energy, then the molecule can jump to the electron can be excited to the higher state. So the electronic state now goes from the E1 to the excited state E2. So that is one important thing. So the only way that the electron can jump from this ground state to the excited state is only if this delta E is equal to h nu, where nu is the frequency of radiation. Now let's take this example. Here we have this molecule. If we take a look only at this particular bond between the two carbon atom, it has got a sigma bond, it has got a pi bond. We will not consider the bonding between this carbon and the hydrogen or with this other carbon. We will consider only between this carbon and this carbon. So what happened here is that we have the sigma bonding, sigma anti-bonding, then we have the pi bonding, pi anti-bonding molecular orbital. Now the same thing here, the energy difference between the pi and the pi star will give you delta E, which is again h nu. So similarly, we can always keep on explaining in the same way for different molecule in this way. Now this has got, between this carbon and oxygen, we have sigma bond just like in the previous case, we have pi bonds just like in the previous case, then the pi anti-bonding, the sigma anti-bonding. Now this is also the energy level difference. One thing to note, you have to remember, is that the sigma bond, they have the lowest energy, the pi has slightly at higher energy. Now the pi star, again at a higher energy, and the sigma anti-bonding, they are the highest in energy level. So apart from that, this oxygen atom also contain non-bonding electron. So we have non-bonding molecular orbital also there. So this is rather a simplified energy diagram of the molecular orbital theory. So here we will also have electron occupying the non-bonding orbital. Now if you look at this energy difference and this energy difference, what do you think? It's rather easy to understand, but let's have a look at a small mathematical thing. We know that delta E equal to h nu, and we know that this nu is the frequency, so we can rewrite the frequency equal to delta E by h. We also know that the frequency equals to c by lambda. Okay, so c is the speed of light here. So we can relate then that lambda equals to hc by delta E. So what does this mean? Now these two are constant, h and c are constant. So it simply means that the wavelength is inversely proportional to the energy differences. So if the energy difference is less, the wavelength will be longer. If the energy difference is large, the wavelength will be smaller or shorter. Similarly, in the same way, you can see that frequency is directly proportional to the energy difference. So the higher the energy difference, the higher the frequency. The lower the energy difference, the lower the frequency. So if we look back between these two, we have the energy difference here. This is delta E2. We can call it as, it is smaller compared to delta E1. Therefore, delta E2 will have less energy than delta E1. So between these two, what you will expect is that the absorption of light here will take place at a shorter wavelength, but here it will be at slightly longer wavelength. Now let's move on about the type of transition. So I hope you are clear about this little bit about molecular orbital theory. What you can see from here is that, let's have a look at a molecule that contain pi electron system and molecules that may contain pi and both non-bonding type of electron system. Now in a molecule containing all the electron system, the sigma, the pi, the non-bonding, there can be these type of transition. So the electron, if you have enough energy, it can jump from the sigma to sigma star, but that is usually very high energy transition. So this is sigma to sigma star. Then you can have a pi to pi star, movement from jumping from there to there, that's known as pi to pi star. Then we can also have n to pi star, so from the non-bonding to the pi anti-bonding molecular orbital. Okay, so we can generalize in this way. The wavelength will be in the opposite way. So where we have lambda E1 will be less than lambda E2, less than lambda E3. Okay. Now in continuation, I have here some of the values. Usually we call it sigma to sigma star, are very high energy transition. So you require a wavelength of around 150 nanometers, very short wavelength, and this happens to be in the high energy UV radiation. The pi to pi star, they are somewhere in 170 to 150 nanometers, slightly longer wavelength, that is in unconjugated alkenes. And sometime in visible region when they are highly conjugated polyenes, like in the previous case we have seen lycopene, beta carotene, they are all absorbing in the visible region. Now the non-bonding to pi star, on the other hand, they absorb around 280 nanometers. So as you can see here, if there are not much conjugation, you'll find that the absorption are all in the UV region, and that's the reason why most of the molecules are not colored, or you cannot see the colors. Now let's continue with this part. Let's have a look at the same molecule earlier. Here we have this molecule. What we will do is that now we will ignore the sigma, because the sigma interaction are the one which are not that important for us. In UV visible, it's mostly the pi to pi star or the n to pi star. Now if we look at these two molecules first, this one we have only one double bond, this we have two conjugated double bonds. The pi to pi star here, the energy difference is this much, but here, because there are 4 p orbital, these 4 p orbital will form 4 different pi molecular orbital, okay, with different energy level. So you can see here now that the pi 2 to pi star 2 energy level has decreased due to the conjugation. So that means this will now be able to absorb at longer wavelength compared to this. If you consider the pi molecular orbital, this highest occupied molecular orbital, or in short is known as the HOMO, is the most important molecular orbital. Next to that is the lowest unoccupied molecular orbital. Now why these two orbitals are important? It is because these two orbitals has the least differences in energy. So if the HOMO to the LUMO difference in energy is low, the molecule will absorb at longer wavelength, but if the difference is high, the molecule will absorb at higher wavelength. So we can also say define each of these molecular orbital by this chi in this case. So when you have two conjugated system, we have 4 different molecular orbital, because we have 4 p orbital. See, this carbon, this carbon, this carbon, each has got a p orbital, and all the p orbital are in conjugation, so they will form molecular orbital. We will have these 4 different energy. The more the conjugation, so the more the number of molecular orbital. So in this case, let's say they are chi 1, chi 2 up to chi 6. Now again 3 pi bonds, so 6 total number of electrons, they will occupy the lowest energy possible. So if you look at these two, the energy difference between chi 2 and chi 3, which is the HOMO and the LUMO of this particular molecule, is slightly higher compared to chi 3 and chi 4, which is, now this is the HOMO of this molecule and this is the LUMO of this molecule. So you can understand, as the more the number of conjugated system, the smaller will be this energy differences, and that will lead us to the absorption shifting from the shorter wavelength more towards the longer wavelength. Let's have a look at these examples so that you can clearly understand about that theory part there. Now if you see here, we have ethene, there's only one double bond there. Then we have 1,3-butadiene, we have 2 double bond, 1,3-hexatriene, 3 double bonds. Now the energy required, or the energy difference, delta E for ethene is 173 kilocalories per mole, which requires a wavelength of 180 nanometers for that amount of energy. So very short wavelength, that's why this appears colorless. If you go here, this is 132 kilocalories per mole, so 217 nanometers, still colorless. 111, see the energy decrease as there's more conjugation, absorb at 258 nanometers. Beta carotene, with this extensive conjugation, energy difference decreased to 91 kilocalories per mole, and it absorbs at 452 nanometers. That is somewhere in the blue region, and that's why you get the complementary color of an orange color. Now Let's have a look at an example that contains non-bonding electron also. 4-methyl 3-pentene 2-one. So we have the energy diagram for this, the molecular orbital diagram. We have the Chi 1, Chi 2, Chi 3, Chi 4 for the pi bond. We will forget about the sigma bond here. But we also have additionally, because this oxygen atom has got non-bonding electrons, so we have the non-bonding electrons there also. So we have all these occupied by electrons. So there can be two possible transitions here. The pi to pi star transition, and it was found that the energy is 121 kilocalories per mole, and the lambda max value or the absorption lambda value is 236 nanometers. We can also have this to this, non-bonding to pi star, 92 kilocalories per mole, 314 nanometers. So you can see that the N to pi star has lower energy compared to the pi to pi star. So with these two examples, two different type of examples, I hope you are clear about the molecular orbital theory. Now let's have a look at the UV visible spectroscopy. How all those things are related to UV visible spectroscopy. So this technique is primarily used to measure multiple bonds or aromatic conjugation within a molecule. The UV region can be from 100 nanometers up to 400 nanometers, and visible region is from 400 to around 800 nanometers. But if you look at this region here, you can see that this region is from the red to the blue, from 800 to 400. Then as you go to 400 to 190 nanometers, this is known as the near UV radiation. Anything beyond this up to 100 nanometers, it's known as vacuum UV. So it's not possible to measure in a common laboratory to take a measurement of 190 to 100 nanometers. The reason is because oxygen molecule in air also, they absorb in this region. So most of the molecule, even a single bond also, sigma bond can also absorb in this region. So these will require vacuum. There should be no air, and it has to be carried out in special laboratories. Most of the UV visible instrument will contain a region from 190 maximum up to 800, so within these regions. Now a UV visible spectrometer looks something like this. So you have your UV visible machine here. It's connected to a controller and then connected to a computer where you can plot a graph. So this is more like an automated system. You don't have to do anything. You put in the sample and the reference sample, and then the system will take care of everything. So how does a UV visible work? I have a schematic diagram here. If we look at this, we have the light source. It can be a D2 lamp. This is a sodium lamp and a tungsten lamp. So all the possible light rays, from UV to visible, can be emitted by this one. Then you have a filter here. A filter means something that allow only one type of radiation to pass through. The rest will be blocked. At a point of time, only a monochromatic radiation is allowed to pass. Now this will then have a beam splitter. It will go through a sample, and part of that will go through a reference. Then you have the sensor here about intensity of light and then how much is absorbed, and then that will be processed by the machine. And finally you have the spectra in this form. So what the machine does is that it automatically keep on changing the wavelength from, say, from 200 to 800, and then it will plot a graph between those regions, and then it will scan and it will know where is the lambda max value. So that is the working of a UV visible spectrometer. A spectra will look something like this. After the machine plot, you see that we have this spectra. So this is the spectra of Congo red, this molecule here. It falls, you can see here two peaks are clearly visible. So we have two lambda max. This is one lambda max and this is a second lambda max. Now the first one is because of the pi to pi star transition. The second one is due to n to pi star transition. This is usually known as the K-band. This is a German word, conjugate. I'm not sure how I pronounce it correctly or not, but it means conjugated. So the K-band, due to the pi to pi star transition, which I have seen earlier, is called as the K-band, or it's due to the presence of all these conjugated double bonds. Now on the other hand, the n to pi star, or also known as the R band, which is a German word again, radical, meaning of course radical means electrons that are not bonded. So you can see here this nitrogen and nitrogen, this contain lone pair on both of these, this nitrogen to nitrogen. So this can also undergo n to pi star transition. Now UV visible spectroscopy is an electron excitation phenomenon. So sometimes it is also called as electronic spectroscopy. You know that it records the wavelength of an absorption maximum, just like we have seen in that graph. So you have the absorption maximum. And one more thing that you see in the graph is that it also records the strength of the absorption. That means the intensity. How much is the intensity of the absorption? That is known as the epsilon max, or the extinction coefficient. So absorption maximum give you lambda max, extinction coefficient give you E max or epsilon max. Now this is defined by the combined B-Lambert's law, which is given here. I'm not going to the detail of that, but let's have a look at this. Epsilon is equal to absorption divided by CL, and I0 here is the intensity of the incident light, and then I is the transmitted light. Log I0 by I is the absorbance A, so that's how you get that A there, or is also known as the optical density. C is the concentration of the solute, and L is the part of length of the sample in centimeters. So we have epsilon is the molar absorptivity. So in simple words, it just simply means epsilon gives you the intensity of the absorption, while lambda max gives you the wavelength of the absorption. In spectroscopy, the higher the intensity, that means it will be an allowed transition. If the intensity is very low, it's called as a forbidden transition. So let's look back at that spectra there. Here we see that the K band has higher intensity than the R band. It was found that the pi to pi star transition are usually intense with the epsilon max value greater than 10,000 because it is an allowed transition. But on the other hand, the n to pi star transition, they are forbidden transition. Therefore, their epsilon max value is usually less than 100. But you might have one question looking at the spectra here. You might see that the R band and the K band in this particular spectra, the difference is rather less. Well, in a conjugated system, if the conjugation is more, it happens that the decrease in energy between the n to pi star also is smaller, getting smaller and smaller. Okay, so because of that, the intensity of the R band also increase when you are in a conjugated system. So it's not only on the K band that you have high intensity, the R band, the more the conjugation, it will also increase the intensity of the R band. Let's have a look at another spectra example. I have taken this from the spectroscopy book by P.S. Kalsi. So we have here the Coles 4in3on. Now you can see here the big difference between the R band and K band. Here the K band of Coles 4in3on, very highly in intensity, whereas the R band is very low in intensity. So the K band is due to the double bond conjugation here, and the R band is due to the N to pi star transition. But still, this is not yet in the visible region, it's still absorbed somewhere in the UV region. Now the second example, that is 4-methyl 3-pentene-2-one, or it's also known as mesetyl oxide. If I place this spectra, you can see side by side, these two molecules have almost the same spectra. If you look closely, that they have very similar functional group. The functional group of both of these molecules is an alpha beta unsaturated ketone. So here we can see that the K band has high intensity, but the R band has low intensity. The reason for this is because the K band is an allowed transition, whereas the R band is a forbidden transition. I'll not go into the detail about allowed and forbidden transitions. You'll learn more about this in physical chemistry classes. So with this, we have come to the conclusion. I hope you are clear about the working principle of UV visible. We have also relooked at the molecular orbital theory and how through this theory you can see that the more the conjugation, the lesser will be the energy differences between the different transition, pi to pi star or n to pi star, and because of that the absorption take place in longer wavelength, and because of the change in absorption to longer wavelength, it might also absorb in the visible region. So even though molecules which are not that conjugated, they absorb in the what is called as in the UV region, but as the molecule conjugation increases, the absorption shifts towards the visible region of the spectrum. So that's all for today. In the next session, we will discuss on the application of UV visible spectroscopy and also on how to use Woodward rules to predict the lambda max of a given molecule. Thank you.